Hello students, welcome back. Let us resume our discussion in section 4. We have to state and prove Gauss Lemma number 1. It goes like this. Let P be not prime and let A and P be relatively prime. In other words, A is non-zero mod P. Then the Legendre symbol A over P is determined by the number of positive integers less than P over 2 with the following property. What is so-called this following property? Well, it's this property here, which I'm highlighting in bold. Among positive integers, 1 through P minus 1 over 2, let K be one of those positive integers less than P over 2, 1, 2, 3, 4, 5, 6 up to P minus 1 over 2. Now that's it, because the next integer is P plus 1 over 2, but that exceeds P over 2. So the number of positive integers less than P over 2, we are talking about the integers here, but not all of them will satisfy this condition here. Let's see, what is this condition? Divide Ka by P and take the remainder. And the remainder has to be always greater than or equal to 0 and less than the divisor P. That's always true. But some of them will be sufficiently large so that it's greater than P over 2. That's what this following property is all about here. So in general, this for everything, but not all of them. Some will be too small, some will be too close to 0. Those are out. Some are sufficiently large. Those are in. And then how many are in? Well, that's the number of element n. And as for this division algorithm, well, you can apply division algorithm at any time, so let us not overemphasize it. Let's go back to the regular font. The key point is this one highlighted in blue. Let's utilize this. Okay, how do we prove this theorem? Step 1, let's have some preparation. So we have the division algorithm, alright? And then our case, greater than or equal to 0, less than P. And then how many K's are there? 1 through P minus 1 over 2, so there are total P minus 1 over 2 candidates. Among them, some are in, some are out. One more observation. Please observe that Ka and Rk are always congruent, modulo P, because P is 0, so that drops out, so we have congruence. Now, in this congruence, we just multiply them all. K's 1, 2, 3, 4, 5, 6 up to P minus 1 over 2. All those. Then what do you get? Well, this is what you're going to get in the left hand side. Multiply them all. 1a, 2a, 3a, 4a up to P minus 1 over 2a for all k. And then right hand side, multiply them all. R1, R2, R3, R4, all those. All Rk's. And then they are congruent modulo P, because for each k, we have congruence. Now the right hand side is all set for the time being. Left hand side, how many a's are there to multiply? Of course, a to the P minus 1 over 2 power, because there are that many different k's. And how about the coefficient? 1, 2, 3, 4, 5, 6 up to P minus 1 over 2. Of course, we get factorial. And one more observation. This quantity here is congruent to Legendre symbol, thanks to all this criterion. So what we get in the left hand side, we got up to here. The right hand side, well, we didn't do anything to the right hand side, but we're going to work out the right hand side in step 2 and step 3. And then eventually, what we aim to do is to prove this through step 2 and step 3. So if you compare this and the original left hand side here, then you can see those factorials drop out. They divide each other out. And what's left is the desired equality. But of course, this is what we have to prove in step 2 and step 3. We didn't do it yet. So for now, that's what we did so far. Now from this point on, let's work out the right hand side, the product of all those remainders. Okay, let's work out the remainders. A is non-zero mod P, so each Ka is distinct from the others, modulo p and also non-zero mod p. Is that clear to you? Maybe not, so let's work out the proof. K times A is non-zero every single time. Why? That's because K is non-zero too. K is selected from 1, 2, 3, 4 and so on, certainly less than P, so none of them is congruent to 0 mod P. So K is non-zero, A is non-zero, and P is prime. So multiply them all, we're going to get non-zero mod P. Modular composite, they may turn out to be 0, they may have some 0 divisors, but for modular P, that never happens. And deep down, we have Euclid lemma. Now, how about distinctness? Well, if I and j are different, then IA and JA are different, modulo P. One way to do that is to subtract from one another and start from I minus j is non-zero. And of course, A is non-zero to begin with, which came from here, of course. So I minus j times A is non-zero, multiply two non-zero numbers, and then break up the parentheses and flip JA to the others. So what do you get? IA and JA are different if I and J are different. So they're all distinct and they're all non-zero. Consequently, all the remainders RKs are distinct and non-zero as well. You see, all those RKs are same as KAs, and then RI is AI, RJ is JA, they're all distinct. So what did you get? All the remainders are all different and all non-zero. Okay, alright, so far so good, but I have to utilize this blue property, and that's the hardest part. Let's begin. Among all those remainders, some are less than p over 2, so they're out. Some are greater than p over 2, so they're in. So we want how many satisfy this blue. Now select any pair. Ri is, we use Ri for those small enough, less than p over 2, and we use Rj for those large enough, greater than p over 2. What if there's anything equal? That'll never happen because p over 2 is not an integer. P is odd prime. Now among those, let's do this computation as well. Ri is less than p over 2. Rj is greater than p over 2, right? And then we just add them up. And how does that help? That's congruent to IA plus JA. Is that clear? Yeah, by the definition. I mean, yeah, they're congruent for I and also J. And then we have I plus J times A. And that's non-zero. Why? Because I plus J is going to be non-zero, you see? I is greater than 0, and actually it would have been better with p over 2, less than p over 2. Same for J, less than p over 2. So the I plus J is greater than 0 and less than p. So no way it is congruent to 0 mod p. So that's non-zero. That's non-zero. Multiply two non-zeros. What do you get? Non-zero. So Ri plus Rj is non-zero. Does it help? Look what comes next. Flip Rj to the other side and you're gonna get this. Ri is different from 0 minus Rj. What did I do? I flipped this Rj to the other side. This is Ri, and then flipped Rj to the other side, alright? But then again, let's make an additional adjustment. 0 is congruent to p. And let's consider different quantity, p minus Rj, and that's different from Ri. That's what you accomplished through this. And then all those are coming from 0 to p over 2, so not only they are incongruent, but they are different. We can drop this third horizontal bar and make this observation. Rj is actually greater than p over 2, but if you do p minus Rj, it's less than p over 2, because if you subtract from p minus p is 0, p minus Rj, and p minus p over 2 is p over 2, and we have to flip the order of all this inequality, we get that. Consequently, what do you get? Let's see. All the Ri's are distinct from one another. All the Rj's are distinct from one another. Consequently, all the greens, P minus Rj's are all distinct from one another. Not only those, even if you cross, Ri's and P minus Rj's are all distinct. They're all distinct from one another, but they're all coming from 0 to P minus 1 over 2. Or more precisely speaking, from 1 to P minus 1 over 2. They're all greater than 0 and less than P over 2. They're all coming from here. How many are there? Total, P minus 1 over 2 different integers. And then how many Ri's and how many P minus Rj's? The same. They all came from these K's, so they're total P minus 1 over 2. And then they're all distinct. They're all coming from here, which means those K's just permute these. You see, the counting technique. They're all coming from here, and then they're all distinct, and then the total is P minus 1 over 2. They have to be the same, just different order. Consequently, if you multiply them all, then ordering does not matter. So it's going to be the same as just plain factorial computation. Oops, I think I skipped a step. No, I didn't skip any step. Yeah, okay, here we go. So multiply them all, then multiply all small remainders, red, multiply all the big remainders, and then small remainders, all those red stay put, nothing changes, and all those big changes to 0 minus Rj, and then times -1, we're going to get this, negative cancelling out. But then again, if you consider mod P, then this becomes P minus Rj, and then we have additional -1 here. And this green here, P minus Rj, and then versus all the Ri's, well, they're all just permuting 1, 2, 3, 4, 5, 6 up to P minus 1 over 2. And then we have a bunch of -1s multiplied. So we have factorial because ordering does not matter anymore. If you're multiplying them all, then permute those, different order, doesn't change anything. Multiplication is commutative. And in here, how many -1s did I multiply? N. The number of blue Rj's, number of big Rj's, number of remainders greater than P over 2. So that's what we got in the right-hand side. The conclusion of step 1 was like this, but right-hand side turned out to be factorial times -1 to the nth power. So what do you get? This factorial here, which was from step 1, and this factorial here, which we got just now from this permuting, the change of order but all those multiplication, and multiplication is commutative, and then -1 to the nth power, the number of sign changes, number of -1s, in other words, number of sufficiently large Rj's, blue Rj's. So after cancellation, oh voila, we get what we want. Legendre is simple. A over P is indeed -1 to the nth power. That completes the proof of Gauss Lemma number 1. And we're going to go ahead to Gauss Lemma number 2 in the next video.